Uh, in this video, I'm going to show you, I guess I'm going to describe a problem to you that's got to do with projectile motion. It'll be quite simple, and we're going to solve the sort of problems in this situation using the impulse momentum theorem. There's going to be two questions associated with one. I don't know. Let me draw you a picture. So here is a ledge or something, or a cliff. I am not putting in how high it is because it's got nothing to do with our problem. You could say this is the end of the world or something like that. But here is the starting position of a projectile, and it's going to take a path that goes up and out, and then loses its vertical motion, gains downwards vertical motion, and then you kind of know how this plays out, right? You get this parabolic path. It doesn't go straight, it continues to curve, and then the direction of motion just gets more and more down directed. What's interesting is you probably remember in projectile motion problems, if you have no drag, no air resistance, then there is no acceleration or gain or loss of motion sideways. It's purely, the motion changes purely downwards. So whatever sideways motion you start with, you just keep it all the time unchanged. Okay, so I'll give you some details. This starting position, it's normally you call it like sub-zero or naught, but I'm going to call it A, and it just kind of goes along with how how I've been presenting the impulse momentum theorem. So this is a special moment in time. It's like the very first moment in time that the object is a genuine projectile. It's right after it was thrown off the ledge. Here is the special moment in time called B, and this is when the object is at its highest location. And you know that what that means is it's lost all of its upward direction motion. So it's neither heading upwards nor downwards. It has just finished heading upwards and is beginning to head downwards, right? Here is a special time called C. It's the moment in time that the little projectile is at the same height that it started with. You'll see that neither of my problems that I'm going to describe solving have anything to do with C, but I just put it in there just so, I don't know, maybe I'll bring up some detail about it. So there's C, and I've got these arrows. I'll explain what the arrows are in just a second. And then this is just some far future time I'll call D, and this is after having fallen and gained a whole bunch of downwards motion. So the arrow that describes the motion down here is quite steep downwards and quite fast looking, right, with a large arrow. Yeah, so these arrows are meant to be velocities. So the velocity at A is this arrow. This is the velocity at B, velocity at C, velocity at D. It's common in these problems to go ahead and specify the initial condition. So this is the initial value of the velocity. And so I've got one. I just made it up. It doesn't really matter what it is. It's 3i hat plus 4j hat. In and of itself, this is a vector that has no physical units. But because the units need to be the units of speed or velocity, and we're in SI world, let's use meters per second. So it starts off with 3 meters per second in the positive I hat direction, right? There's a plus sign in there, but it's not explicit, but it's still there. And then 4 meters per second in the Y direction. And on the side, let's put that upwards is positive j hat and rightwards is positive I hat. So yeah, this is over 3 up 4 meters per second. That's that arrow there. we'll also say that the mass of the object is 2 kilograms. And then we're also going to take g is 9.8 meters per second squared. And this right here is the magnitude of the gravitation, acceleration due to gravity. It's just the magnitude. We'll use it as a vector later, but anyhow, here's some details. So g is the acceleration due to gravity everywhere, right? At all points along the path, that's the acceleration due to gravity for this object. Okay, so let's see. Let me tell you what our first problem is. So let's say this is problem number 1. It's got to do with these initial conditions and this situation here. It's a situation of projectile motion. The first question is if the time associated with the ball being here, the projectile being there, if t sub d is 4 seconds after t sub a, which is the time, it's the beginning of the projectile motion, the time at which the projectile has that velocity there. The question is, what is, yeah, let's just do it like this. What is p, the momentum, at the time d? And I'm going to use the Impulse Momentum Theorem to solve this problem. So what is p sub d? So the Impulse Momentum Theorem, it's really easy to write down, but in and of itself, when you write it down, it's actually not useful at all. Let me show you what I mean. It says that the change in the momentum of an object is equal to the net impulse delivered to the object. That's what it says. That's simply the theorem. So we have to figure out, like, I've got this kind of information, I have this problem, and I want to use this to get me the value of p sub d. So what I'm going to do is I'm going to try to figure out how to use this. This is my tool, right? Let's use it. In order to use it, I have to figure out how to use it. So let me think, delta p. So delta p is a change in momentum. It's like a momentum final minus momentum initial. Sometimes it's like that. Or it's a momentum at some second place minus some momentum at a first place. So initial, final, 2 and 1, it's beginning to look like I would like this f, or that 2, to be p sub d, where the I, or the 1, must be about something 4 seconds ago. So yeah, it's probably obvious to you now that we've sort of untangled what's inside of the theorem, but let's ask the theorem to apply to our situation. So we want to know, let's see if this helps. Let's say that delta p that I am curious about is from A up to D. So this is the net impulse that's delivered to this object between the times A and D. So I'm going to put a little signifier that says this is the net impulse that gets you from A to D, or that happens from A to D. So can you see how I started with this, which had nothing to do with my problem in particular, and now I'm figuring out how to use it to apply to my problem in particular. And so far, what I've got is the momentum in at time D, or position D, is the net impulse from A to D plus the momentum at A. And if I get here, I want to know, can I continue? And the answer is, well, I can continue if I can calculate this and I can calculate that. Because if I can calculate these two things, I know how to add vectors. And then once I add them, I know the answer, right? So can I continue? Well, can I discover the value of this? Answer is yes. Can I discover the value of this? I'm going to put question marks because this is actually really tough. This, though, I hope that you agree that this is actually easy. It's easy because in order to calculate the momentum, all I need to know is the mass and the velocity when this is appropriate. So piece of A is equal to the mass, and this is kind of a strange thing to write, but it's the mass when the object is there times the velocity when the object is there. And the mass when the object is there presumably is not different when the object is anywhere else. It's just this constant value of 2 kilograms. I know that's kind of dumb, but you know, in your future of rocket ships, the mass can change, so you can, that's an issue. But it's not an issue for us. So this is 2 kilograms times this velocity. So it's times 3 I hat plus 4 j hat meters per second. So heck yeah, done with that part. So I know how to calculate this. But j net from A to D let's do some exploration. As a student, you wouldn't see through to the end. So all you got to do is start working, don't make any mistakes, and see if you can get to something you can use to finish. If it turns out that you can't because the math is too hard, or there is something that you do not know but you need in order to finish it, then possibly you're in a situation that wasn't the right direction to start from, and you need to backtrack and start in a different direction. And by doing this, you actually learn a lot. You learn a lot by making the mistake of getting yourself into a position that you don't know how to reconcile. Yeah. So you have to then, you have a new problem to solve. You have to solve the problem of that irreconcilable thing that you got to. Okay, but anyways, let's follow our nose. So this, by definition, is going from time A to time D using the net force on the object. The object is the 2 kilogram object, right? So I want to know the net force, and I need to integrate it in time. So T sub A, I don't know. I don't know T sub A. It doesn't tell me that T sub A is 1 second or 5 seconds or 50 seconds. T sub D, I don't know that value either. What I do know, though, in the problem, it specifies that T sub D, whatever it is simply 4 seconds bigger than T sub A. That's what I do know. So secretly, I'm just going to keep a note for myself. This is the difference between T sub D and T sub A, and it's 4 seconds of difference. So I'll just put that aside. I'm not sure if it's necessarily useful yet, but I got it there. It's the time from A up to D, kind of in a similar symbolic language. All right,